Okay, let's get started. Thank you all for being here. This is a very special last cognition colloquium of the semester since it's Gaia's exit talk. Gaia has completed all her requirements for her PhD in psychology with a designated emphasis in cognitive sciences. This is the last requirement, although it's a celebration of her research, not a defense the way there is somewhere else. So we're really here to enjoy everything that she's contributed to science in the past 4.5 years in the lab. It's really my pleasure to introduce Gaia. Gaia came to the lab. She already had a Bachelor of Science in Neuroscience from King's College in London and a master's degree from UCL in London too, where she ranked both in both of them best student. And she's followed that trend in the past years by getting lots of honors and awards that I'm not going to list all, otherwise you wouldn't have time for her presentation. She's been very successful. She's published in many peer-reviewed journal, including PLOS Biology at NeurIPS and others. And she also made quite a name for herself with lots of invited talks, contributing to the community through peer reviewing, through being organizer of various workshops, special editions, etc. More personally, she's been a wonderful person to have in the lab. She's really helped scientifically expand our research direction in the domain of goals. And also she's been just a wonderful collaborator, someone to discuss, someone who never, let things slide. So it was very good to have that contribution. So I hope you will all enjoy her contributions. She's also, as you can see, a talented artist. This is the cover page of the PLOS biology edition in which her paper was published. She just did this. I'm very impressed, but apparently it runs in the family, so. We're happy that she's staying a little bit longer, unsure until when. And of course, we look forward to seeing what happens next. But in the meantime, I hope you all enjoy learning about her research. We would like to keep questions generally for the end, if possible. If there's a pressing clarification question, feel free to interrupt. Otherwise, let's give ourselves just a chance to discuss and ask broader questions towards the end. Thank you.
Thank you. All right, well, thank you so much, Anne, for the wonderful introduction. And I'm excited to tell you all about my research that I did here as part of my PhD about goals as a key for flexible learning. So many animal behaviors are driven by primary rewards, things like food, water, or shelter that we've evolved to value and pursue because they optimize survival. Over time, we can also form association with secondary rewards, things like money or numeric points, which we learn to value because they can yield more primary rewards. But many of the activities that define what it really means to be human seem to have a very loose relationship or are sometimes even in contrast with our evolutionary constraints. Think, for example, climbing up the top of a mountain or creating beautiful art or earning a PhD. So the question that drove much of my research here at UC Berkeley was, how is it that we can learn to do all these things? I've been studying learning from the perspective of reinforcement learning, or RL for short. In the standard RL framework, we have an agent that interacts with the environment. When I say agent, I mean the system that we're interested in modeling. In my case, it's often going to be a person, but it could also be an animal, a robot, and so on. The environment is the part of the world that the agent interacts with. And the environment provides a state. For example, these different slot machines that the agent could interact with. The agent has internal value estimates and a policy. The policy is a set of rules that governs how you turn these value estimates into an action that you select. So in this example, the agent's policy chose the slot machine on the left. Then the environment provides an outcome. In this case, the agent got 18 points. In this specific setup, the agent can see it could have gotten more points if it had picked a different slot machine. This information about the outcome is then used by the agent to update its internal value estimates through a reward signal here in green. And this is very important because when the environment provides the next state, such as this new slot machine situation, the updated value estimates can guide the agent to select a choice that is more likely to get the agent more points, like the slot machine on the right. And then the cycle begins again. So this RL framework is very simple, but also very powerful. It's been able to explain neural data, behavioral data, and even inspire the creation of intelligent agents that beat human experts at complex games like Go. But one limitation of RL, as I described it so far, is that it assumes that rewards are predefined. So in the case of biological agents, we often just assume that there's a direct connection from outcomes to rewards. And in the case of artificial agents, then there's an engineer whose entire job is to create a function that maps outcomes to reward signals. But animals, and humans in particular, are extremely flexible at deciding what counts as a reward and use their goals to do so. So here I define goals as mental representations of a future state an agent is motivated to realize. And so, for example, take these two skiers who are presented with virtually the exact same scenario of the slope ahead of them. The skier on the left wants to meet their friend, and the skier on the right wants to win a slalom race. So the only difference between the two is that they have different goals. And this matters for how they will experience reward. So the skier on the left will find it rewarding to see their friend, perhaps receiving a stronger and stronger reward signal as they approach them, whereas the skier on the right will find it rewarding to arrive at the end of the slope early on, as signaled by the stopwatch at the end of the slope, which the skier on the left may not be noticing at all. So my doctoral research centered around three main questions. The first one is about how our goals affect what counts as a reward and how this process impacts our learning. The second one is about the cognitive mechanisms that allow us to flexibly attribute value according to our goals. Third one is, given that our goals are so important to us, how is it that we select them in the first place? So let's begin with the first one. How do our goals impact the way in which we learn? To tackle this, we focused on a particular decision-making phenomenon called context-sensitive valuation. And context-sensitive valuation or context-dependent valuation is a phenomenon in which the value of an outcome depends on that of the alternatives. And so since some of you may not have heard about this before, let me walk you through an example. So imagine you go to your usual restaurant, which normally serves two flavors of ice cream as dessert, chocolate and vanilla. And in the circles here, I'm showing the absolute values of how much you like them from 0 to 1. So you go ahead, excitedly order chocolate, which you like a lot more than vanilla. And at first, you're very happy with your order, until suddenly you find out that today they're also serving pistachio, which you like even more than chocolate. So if subjective reward was just aligned with the absolute values of how much you like something, you should still be pretty happy. But the fact that the context has changed also changed how much you value the current outcome. So how do we explain this phenomenon? When we first began our study, the state of the art was a model called range adaptation. And this model builds value as a function of the absolute value that you attribute to an option, but also the minimum and maximum values in a choice set. So in practice, you take the absolute value, remove the minimum, and divide by the range. And this leads to a reward of 1 when chocolate is the best available option. What happens when pistachio is also available is the absolute value hasn't changed, but what has changed is the range. And so when you divide by that range, the value decreases. We thought that there could be also a different explanation for this. we consider the possibility that on top of the absolute value, people also have internal signals that tell them whether they achieved their goal or not. So when chocolate is the best option, you still get an absolute reward of 0.7 in this case. But then on top of that, you also have an additional signal that says, great, I chose the best possible flavor. I reached my goal. When pistachio is also available, the absolute value hasn't changed, but what has changed is whether or not you achieved your goal. So in this case, you haven't, and the overall value decreases. To formalize this theory, we use different variants of a standard reinforcement learning model. So all models share the same basic architecture of a simple agent, which learns the value of a chosen option C within a set S over time by calculating the difference between the expected outcome and the experienced outcome, and then applies this to the previous estimate, learning over time. The parameter alpha, or the learning rate, determines how fast you update your expectations in face of observations. And a similar rule also applies to unchosen options for which the participant can observe the outcomes. Then your policy is the softmax function, which basically makes the agent more likely to choose options with higher values. What changed across models was how to define rewards. So in the base model, rewards are simply the absolute values. So this model is very simple, but it cannot explain context sensitivity because it will always value options the same way. It will always think chocolate is the same reward. The range adaptation model I told you about rescale rewards based on the range of available values in a given context, and then uses these range adapted values to update Q-value estimates on each trial. Our intrinsically enhanced model combines the feedback from each trial with a binary internally generated signal obtained by comparing the current reward to the maximum for a context, or to the alternatives if they're known. So what we can then do with these models is we can fit them to participants' data and also use them to simulate participants' behavior and compare which model better resembles the human data that we collect. And we compared how well these models predicted about 1,000 people's choices in 7 different experiments. Here we'll show you the results from one of them. So in this particular experiment, participants performed a decision-making task, much like the slot machines I showed you before, in which they picked one of the available abstract images and received complete feedback. Choices belong to 2 contexts, and in the learning phase of the experiment, people only made choices within their corresponding context. Both context 1 at the top and context 2 at the bottom had 3 options, each having a mean value of 14, 50, or 86, which I'll refer to as the low, middle, and high value option, or L, M, and H. The context differed in the frequency with which different combinations of stimuli were presented during the learning phase. So on a given trial, all 3 options for a given context could be available, or just 2. If you focus on the gray shaded area in the middle, well, option M1 was presented for 20 times against option L1, so the low value option of context 1. Option M2, or the middle value option of context 2, was presented 20 times against the high value option of the same context. So intuitively, this means that the mean value option of context 1, or M1, achieves the participant's goal of selecting the best possible option more times. And so our intrinsically enhanced model predicts that participants will prefer M1 compared to M2, even though their expected values are identical. By contrast, the range adaptation model shouldn't distinguish between the 2 because the range has not changed. It's always the same. Then what we do at test is we have people compare against each of the possible options without feedback. So we collect their preferences. At the very end of the experiment, we also just asked participants, how much do you think this option is worth? And as you can see, people rated M1 as being of a higher value than M2, even though, again, the 2 options are identical in terms of expected value. Here, I'm also showing the results from the test phase where choices were made out of context. And both behavioral results and computational modeling support that the intrinsically enhanced model in purple over the range adaptation model in teal. In particular, you can see that people chose M1 more often than M2 as predicted by our model, but not the competing one. Here I'm showing test trials where M1 was pitted specifically against M2, and you can see that people chose M1 more often, again, predicted by our model, but not the range adaptation one. And when we look at choices against either low option, people were better at picking the optimal M option that came from context 1 compared to context 2. And the inverse was true for choices against higher options. We can also measure how well each model fits our participants' data through this quantitative measure of responsibility. And you can think about it like a measure of how well each model fits or explains the participants' data. So the plot on the left shows each participant as one bar, and the color indicates how much each model explains that participant's data. And the plot on the right is just showing the overall responsibility scores for each model. And you can see that model fitting favors the intrinsically enhanced model, which has a higher responsibility across participants. So in this project, we learned that goals can significantly impact the way in which we define a reward. And in particular, people seem to enhance absolute values with subjective measures of goal achievement. So this teaches us that taking goals into account could help us better predict people's learning and decision-making, even when their choices seem perhaps a little irrational at first. So let's now turn to the second question. What cognitive mechanisms allow for for goal-dependent evaluation? So for primary reinforcers, we typically assume hardwired connections between external stimuli and internal rewards. Even a baby will count water as a reward. If they're thirsty, they don't need to learn this. Secondary reinforcers, we think, work through a learned association with primary rewards. So at some point, you learn that money could get you lots of goods and services, and so now you value money in and of itself through this learned association. But many things in life feel rewarding even if they have no direct or learned tie to the things that enhance our survival. So how do we set these goal-dependent rewards? Our hypothesis is that setting these goal-dependent rewards arbitrarily involves two separate memory processes. So on the one hand, we have working memory and other executive resources, which are precise but capacity limited. So think of this memory system as the one that allows you to remember your one-time password just until you're done typing it. On the other hand, we have long-term memory, which contains more condensed information but can be retrieved without added cost. So perhaps more implicitly, so think about it like the memory that supports your typing of that one password you've had for 10 years and can retrieve without any effort. So when we're learning something new, working memory needs to hold some task information in mind, things about what states are possible, what actions you can perform that allow you to perform the task. When we also have an arbitrary goal compared to a primary or a secondary reward in the task, that goal also needs to be maintained. And then working memory can perform a matching process to compare new observation to the goal we had in mind, turning that into a reward. This allows for flexibility. It means anything can be turned into a reward given a specific goal, which is something that many animals may not be capable of, and which is currently lacking from many advanced machine learning algorithms. But because working memory is capacity limited, this holding the goal in working memory makes the learning process itself a bit less efficient. If the goal space is consistent enough over time, then what we can do is we can start transferring its trace from working memory to long-term memory, where a compressed reward function can be stored and retrieved from. Once we have this reward function in place, we no longer need to resort to working memory for goal-dependent evaluation. And this means the task information representation can be more precise and learning can improve. To give a concrete example, imagine you're learning how to make pots out of clay. Each day, you have a different task to complete where you are given a different pot of a different shape. At first, you need to keep comparing your pot to these goal pots to know if you're doing a good job. Eventually, though, you may have internalized some rules that make for a good pot. And so, for example, you know you're doing a good job if your pot has no bubbles, has a smooth surface, even wall thickness, and so on. And at that point, you no longer need to keep an active representation of the goal in mind. But since pottery experiments are a bit hard to run in the lab, we resorted to this variant of Anne Collins's RLWM task. Here there are two conditions, points and goals. The points condition is a typical stimulus association task with 6 stimuli per block. On each trial, you first see a screen with 2 possible outcomes, win and lose, and then you see a stimulus, in this case, the Statue of Liberty, and you're supposed to pick one of the 3 keys available to you on the keyboard. If you select the correct key for the stimulus, you get 1 point, otherwise you get 0 points. If you get the good outcome, for example, 1 point, then you also need to collect it by pressing a dedicated button. And that's how we know whether you realize you got that you got the good outcome or not. And this is obviously trivial to do in a points condition, but not so much in the goals condition. Here you first see 2 abstract images, one labeled goal, the other one labeled non-goal. Then, just like in the points condition, you see a stimulus, pick a key, and receive feedback. This time, you see one of the outcome images without the label. This requires you to hold the current goal in working memory until you observe the outcome, unless you have somehow internalized a rule for what makes an outcome a reward, and then you can just use that at the time of receiving an outcome. Each block consists of 6 different stimuli, each repeated 12 times. And on each trial of the goals condition, the specific goal and non-goal images could also change. Each participant also completed 2 points and 4 goals blocks. We ran 6 different experiments, and what varied across these experiments was the goal and non-goal contingency, so how we set these goal and non-goal images, but the structure was the same across all 6 experiments. In the particular experiment I will talk about today, we kept the number of goals identical across 2 different types of blocks. The goal images were geometric shapes, which could take one of 2 forms, one of 2 colors, and one of 2 filling types, leading to 8 distinct images in total per block. Unbeknownst to participants, the compressible goals condition had goal images share one feature, in this case, the filling type. In the incompressible goals condition, blocks were built in such a way that no simple rule could be identified. And so this required participants to constantly hold the current goal in working memory. And so we predicted that learning would be more efficient in the compressible goals condition compared to the non-compressible goals condition. This was not a given. It was not a guarantee, because different models could make different predictions in this setup. For example, if you think that people can just effortlessly attribute value to any outcome on the fly, then without incurring any cognitive costs, then performance should not differ across the conditions. If you think people attribute value to arbitrary outcomes on the fly, but that does have some cognitive costs, then we should see a decrease in performance from points to goals, but then no difference between the 2 goals conditions. Only our reward function compression model predicts that over time, reward assignments will become more efficient, freeing up resources that can be then used for learning. So we expected people to do better in the compressible compared to the incompressible goal condition. And that is exactly what we found. So performance was best when learning directly from secondary outcomes, in our case, points, but it was better in the compressible compared to the incompressible goals condition. To verify our reward function compression hypothesis a little bit further, we ran an additional test. So remember that our experiment had this embedded go, no go task in which we called reward collection. And we thought that if reward function compression eliminates the need for pattern matching upon receiving an outcome, then we should see that participants who are faster at reward collection also perform better in the learning task. And that's exactly what we see. The smaller the difference in reward collection between the compressible and incompressible goals condition, the smaller the difference in the respective learning condition. To look more closely at the underlying cognitive mechanism, we modeled the learning process through a simple model similar to the one I showed you earlier. One difference is that we kept the temperature fixed in the softmax function, and we added some random noise in the decision process. We also added a few other factors that I'm happy to share later if you're interested, but this is the essence of it. And then to test whether reward function compression specifically affects the learning process, we created a model where the learning rate alpha is modulated by the speed of reward collection. We then compared this against two other candidate models. One where learning rate depends on the task condition, but not the reward collection speed. And one where the noise in choice selection rather than learning updates is affected by reward collection speed. So the blue and yellow models test slightly more nuanced questions about how reward function compression specifically affects learning, and the pink model is more of a baseline. What we find is that the model with a learning rate affected by reward collection speed is the best one. And here you can see the relative AIC scores for each participant, where lower means better. What we can do is we can verify that our model replicates the desired behavior. And indeed, we find that it matches the overall pattern of results we observed in the data. So the overlay triangles here are showing model simulations over the actual participants' behavior. In the paper, we have 5 more experiments and additional tests that further confirm our hypothesis, but I'll save this for another time. So in this project, we showed that humans can learn to achieve new goals very flexibly, but with cognitive costs due to capacity constraints in working memory. When the goal space can be compressed, a simple reward function can be transferred from the limited working memory to more efficient long-term memory. And this frees up critical working memory resources that lead to improved learning speed and overall performance. So far, we've seen that our goals are crucial to determine what counts as a reward. And as a result, they affect our learning and decision-making. So the next question for me was, how do we select these goals in the first place? There are many reasons why one might pursue a goal. So take, for example, the goal of becoming a doctor. You may want to do this because setting such a goal could give you a good salary. Or perhaps you could just imitate other people as a proxy for what a good goal might be. So for example, you may want to be a doctor because your mom is. Sometimes we also explore goals a bit more randomly, especially in low-risk situations. We might just do things because. Other times, our exploration is guided by the hope to learn something new. And it is this type of goal setting that I studied in my next project. So the vast majority of human studies have an experimenter decide which goals the participants should pursue, and then that's what defines the task. It's a lot rarer to find a case where goal selection is the actual dependent variable that is the object of study. So here we developed an alchemy game where people could learn how to make various potions to measure just that, how people decide which goals to pursue. Each trial in the task consisted of a goal selection phase in which participants selected a potion, an action selection stage in which they chose either 2 or 4 available ingredients to make the target potion, and a feedback stage in which the target potion's flask either filled up or remained empty. And this was determined by whether the set and order of ingredients participants selected was correct. So to show you what the experiment looked like to our participants, they began by reading some instructions on their computer. And then here you're actually seeing the training stage in which they can only select one of the available goals. In reality, in most of the tasks, people could select potions freely. And so you can see they first select a potion, then they're given a bunch of ingredients to put in a certain order that they need to try. And then they receive feedback based on whether they selected the correct order. So if and when they do the correct combination, they get positive feedback. 2 key aspects were manipulated across potions: difficulty level and hierarchical structure. So let's start with difficulty. Here you can see that 2 potions, G1 and G2 for goal 1 and goal 2, had solutions that required only 2 ingredients out of the 4 ingredients participants were given. And so in this example, it corresponded to the teal and orange potions. To manipulate difficulty, we introduced 2 other potions, G3 and G4, which in this example correspond to the purple and gray potions. And were made of 4 ingredients, not 2, so the solution was harder to find. To introduce hierarchy, we secretly built the solution for G3 in such a way that would correspond to the solution of G1, followed by the solution of G2. And by contrast, G4 had no corresponding hierarchical relationship to any other potion. So to ensure we could separately measure the effects of hierarchy from those of difficulty, we introduced 2 final potions. And so here we have G5 and G6, which were also made of 2 ingredients, but this time the ingredients themselves were other pre-made potions. So G5 and G6 share the colors of G3 and G4, and correspondingly, G5 was made of G1 followed by G2, while G6 had no hierarchical relationship with other potions. Based on the existing literature, we made a prediction that people's goal selection would be partially guided by their performance, either by avoiding tasks that they already know how to complete or getting pleasure from positive feedback. We also wanted to see if hierarchy itself would impact goal selection. And we were particularly interested in whether people's goal selection would be guided by learning progress, which is a powerful signal that is often used to build artificial agents that direct their own learning and has also been found to be meaningful for humans selecting which tasks to engage in. And so learning progress can be formalized in many different ways, but you can think about it as the derivative of performance. So how much your performance changes over time. And the idea is that you want to choose goals that are neither too easy nor too hard, and learning progress can help you get there. But people can perceive progress even in the absence of apparent changes in performance. So we coined the term latent learning progress to distinguish this case. To show you what I mean by learning progress and its latent version, let's go through an example from our task. Let's say you have chosen this purple potion as your current goal, and you're given 4 ingredients to try and make it. You must use them all in the correct order to successfully create the potion. So you try a simple sequence without luck. On the second trial, you decide to pick the same goal again and try a new combination, again without success. You try this again and again until eventually you succeed. According to the standard definition of learning progress, it is only now that it's kicking in. And so the literature suggests you would use this signal to guide your goal selection. But since you know the space of possibilities is limited to the various combinations of the different ingredients, every time you try a new combination, you're essentially making progress through a process of elimination, even if you don't observe changes in your actual performance. Since this type of progress comes before you observe any changes in performance, we call it latent learning progress. And here we're interested in whether latent learning progress, or LLP for short, guides people's goal selection perhaps better than the standard LP measure. First, we needed to validate our new experimental design, and so we looked at participants' behavior as a whole. And recall how in building our experimental environment, we manipulated goals difficulty levels and hierarchical dependencies. We found that both of these variables had significant effects. So people were better at making potions that required only 2 ingredients compared to ones that required 4. And people were also better at making potions which shared structural similarities with others. We found the opposite pattern for goal selection. People spent more time trying to achieve harder potions and less time on hierarchical potions, presumably because they solved them faster. We then took a closer look at individuals' behavior and found different types of learners. So each of the plots I'm going to show you illustrates one participant's behavior over the duration of the experiment. So the x-axis represents the trial number, and the y-axis the specific combination of ingredients the participant selected. Dots are color-coded by goals and filled if the participant got the positive feedback, empty if the ingredient combination was wrong. So if you think that goals and rewards are the same thing, then one rational approach to this task would be to find the solution to at least one potion and then just spend the rest of your time maximizing positive feedback by just doing that specific potion over and over. And one or two participants did that indeed, selecting the same successful potion over 100 times. But we also find that that's boring. And so most people don't actually do that. Another potential strategy is to just randomly pick ingredients and potions, spending very little effort on the task. And again, maybe some people do it. After all, it's not like we're paying them more if they get more potions or anything like that. So why bother? But once again, only a very small group of people actually does that. Instead, what we find that most people do is they put considerable effort into try and learn all of the potions. So many of them spend the first half of the experiment learning how to solve each goal, and then training themselves on each individual one. And so this pattern of goal selection, where people stuck to one goal and tested possible combinations until they found a solution, was also very common. They also tended to be quite specific in how they were testing different hypotheses. So they tended to systematically test various combinations of ingredients in order. And this allowed them to just remember the very last combination of ingredients that they tried rather than all the possible things they have checked and remain to be checked. So we next turn to modeling once again to help us understand what key variables explain these behaviors. So we built sequential models of goal selection in which that relied on either one or a combination of the motives that we were interested in. And we model human goal selection as a multi-arm bandit problem, where the probability of selecting a goal depends on its subjective value relative to the other goals, again, through a softmax. We keep score of how much each goal satisfies each model's value, symbolized by V here. And goal values are updated based on feedback through the delta rule. But how you integrate feedback depends on the model. So different models care about different aspects of the learning process. For performance, it's easy. You get a +1 when you get positive feedback and +0 for getting negative feedback. So over time, goals where you tend to do better get higher values. And then you pick them more or less often, depending on the weight you assigned to the specific beta value for this model. For hierarchy, you increase the value of a chosen goal if it has a hierarchical structure, decrease it if it doesn't, and then keep it at 0 for simple goals. Learning progress is based on how much you improved relative to how much you thought you would improve, so your previous estimate of learning progress. And latent learning progress is based on how many of the possible action sequences you've tested and goes down to 0 once a solution has been found. We then compared models where goal values were updated based on one or more of these features. Here you're seeing the responsibility measure I showed in the other plot, and we found that across participants, LLP, or latent learning progress, was a very important factor for guiding goal selection, better capturing behavior than the alternative models that didn't care about this signal. And so here you're seeing again responsibility. You can see that models with LLP tend to do best. We also did some clustering analyses and found that this was true, even though the resulting behaviors seem very different. And we think this is because LLP interacts with individual learning, but all participants seem to care about this signal. So through this project, we learned that latent learning progress is a powerful signal that guides human goal selection, at least in certain settings. We also learned that hierarchy plays a central role, but it remains a bit unclear still if it does so directly by operating on goal selection or indirectly through learning. We also found large inter-individual differences in behavior, and in future studies, we may try and relate these different behaviors to other aspects of their personality and motivation. So to summarize, we saw that goals can directly impact how we define a reward, which in turn affects our decisions. We also learned how different memory systems work together to support our ability to learn through reinforcement from arbitrary outcomes. And we also found that latent learning progress guides goal selection in intrinsically motivated individuals. Now I want to take a step back and talk about how these concepts fit within the broader academic discourse and about their application. So my doctoral work emphasized the necessity for a paradigm shift in human studies where, because goals are so central to cognition, it's worth studying goals in and of themselves. The research I showed you today is not at all comprehensive, and there are many interesting directions to pursue, some of which I'm already working on. So I'm continuing work on reward function compression with TFAN to see if our theory holds true in different settings. And I'm also studying how individuals' goal selection might be important for building advanced societies. So with Jeremy and others, we're proposing a role for goals in cultural evolution. In my work with Moshe, I also showed that even imaginary goals matter because they help us innovate and prepare for future situations. The fact that people can select their own goals doesn't necessarily mean that they always make optimal decisions. And so sometimes they keep selecting a goal they would be better off abandoning, for example, in gambling. So with Ali, we have some work trying to understand why people show goal persistence biases. Goals can also significantly impact our emotional lives. So with Bastian, we're trying to figure out how exactly this works. And to try and create a common language among scientists studying goal dynamics, I'm editing a special issue of the Topics journal with Cedric, Joni, and Robert. There are many ways in which this work can be applied down the line. If we better understand what makes it easier or harder for people to achieve their goals, then we can improve our educational and public policy strategies to help people become their best selves. We can also help people change goals when these become maladaptive. So with Zach Pardos and others, I'm testing whether personalizing online learning environments helps people learn skills that will serve them better in the future. AI research could also benefit from this work. For example, by borrowing the insight that learning is made up of different learning systems that have different trade-offs rather than a single algorithm to master any skill. Our work also shows the importance of self-driven learning. So this is quite different from most AI systems today that learn to optimize a pre-specified function. Creating intelligent robots, for example, capable of going to a different planet and exploring the environment will likely require artificial agents that set their own goals, much like humans do. We can also borrow tools from cognitive science to better understand advanced AI systems, replacing the black box of the brain with the black box of language models. And this is something I'm actively pursuing with Danielle and Dave at Amazon. So I just want to say one more thing before I thank you all for listening so far. Here I focused on individual learning and looking at how people learn on their own. But in the real world, we accomplish our most impressive goals with the help of others, not alone. And I wouldn't be here standing in front of you today getting my PhD if I didn't have an amazing support team with me. This is the hardest part. Okay. So I am immensely grateful to my PhD advisor, Anne Collins, for welcoming me to her lab from all the way across the world. Anne is one of the smartest people I know, but also incredibly kind, human, fun, and all around the most supportive mentor I've ever had. I couldn't have asked for a better person to work with for the past 4.5 years. And they say people don't leave their jobs, they leave bad managers. And if that were true, I would never leave. To Pierre Boudelier, I owe some of the most intellectually stimulating periods of my life and career. So thank you for allowing me to explore new ventures through your group. I would also like to thank my other doctoral committee members, Rich Ivory and Bill Thompson, and my pre-doctoral committee members, Amitai Shanav, Steve Piantadosi, and Joni Wallace for providing me with their perspectives and encouragement. To my past mentors, Tali Shaot, Moshe Bar, Charlotte Russell, Iri Borman, and Ken Britton, thank you for the opportunity to learn under your wing and for setting me on the path that brought me to this dissertation. I would not have been able to do some of my doctoral work without my collaborations, some of which are on this slide. So thank you for your hard work, words of advice, and openness to feedback. But above all, thank you for letting me learn with and from you. To all my past and present colleagues at the CCN lab and friends in the psychology department at Berkeley, thank you for joining me in this fantastic journey. I'm so glad I got to share it with you. To Flowers Lab team members, with whom I got to spend a semester with and continue collaborating. Thank you for all the laughter and fun conversations. I hope we cross paths again. To my coworkers from the computational social science team at Meta, thank you for teaching me about impactful work in industry and letting me learn from you. To my new friends from the Amazon AGI labs, thank you for inspiring me with your eagerness to learn. To the countless other people I met at conferences, summer schools, and work trips around the world, thank you for sharing your thoughts, helping me improve, and making academia the collaborative community it has been for me. Many old friends contributed to making my PhD journey a joyful experience by supporting me from afar. To my forever best friend, Francesca, thank you for being my rock, my shoulder, my companion all the way through. To all my closest friends, too many to mention, thank you for inspiring me through your unique ways of being, for always rooting for me, and for warming my heart with your invaluable friendship. I don't know what I'd do without you. I'm also grateful for the people who helped me feel more at home since I moved here to Berkeley. So thank you, Jan and Dan, for opening the doors to your family when I couldn't be around mine. And thank you to all the people I became friends with after I moved here for adding depth and meaning to my international experience. I could not have come this far without the unconditional love and support of my family. To my close relatives in Italy and Israel, thank you for bearing with my long absences and for always welcoming me back with pure joy. To my grandparents, Silvana and Armando, thank you for being such incredible role models and passing down the values I live by today. Having you as my safety net has enabled me to follow my curiosity without fear. To my brother, Danny, thanks for reminding me to enjoy life, even in the toughest moments of my doctoral journey, and for filling mine with so much happiness. To my parents, Enrico and Michal, thank you for joining. Thank you for giving me the freedom to aim high and the help to get there. Thank you for your encouragement, practical advice, and constant love. Thank you for holding my hand when I needed it and for letting it go when I felt ready. Thank you for nurturing me and allowing me to blossom. No words can describe my gratitude and love for you both. To my partner in life, Josh, thank you for accompanying me every step of the way and for wanting to be in my future. Thank you for sharing all the joys with me and comforting me in darker times. Thanks for being my ally, friend, and #1 fan while helping me become a better person each day. I love you so very much. And that's the end. Thank you. And I'll take any questions from the audience.
Great talk and beautiful slides.
Thank you.
I just wanted to ask about, I'm going to apply experiment too, but the second study that you talked about where
Yeah.
you had that very comprehensive learning versus comprehensible learning. I was wondering if you ever thought about like I was looking at like the comprehensive and incomprehensible one, but they start off like around the same,
Mhm.
right? And then
Yeah.
it kind of like
Yeah.
skyrockets a little bit. And I'm wondering if I think what you were suggesting is that they learned some global feature about the goal. I'm wondering if you were to change that, how long would it take them to kind of get back to where they were? In this case, like let's say the solids, you do have to experiment with solids as being the goal, and then halfway through you flip it to the non-filled states.
Yeah.
Do you think, like, would they be able to quickly adapt, or do you think some of that, now that memories in long-term memory, do you think that would affect trying to learn the new goal, especially since it's the other way around?
Yeah. So for people on Zoom, I'll repeat the question. It was about study 2 and the temporal dynamics of reward function compression and what happens if you change the rule that makes goals valuable. So I don't have a direct answer to that, but we didn't tell participants about the different goals conditions. And what we found is that people tend to figure this out over time, and that's why they start at the same place, and then over time they're able to compress that rule and integrate it into long-term memory. We also had 2 blocks of each, and if you just look, I don't think I have it here, but if you just look at performance in the second block, it's almost the same as the points. So I would expect that people are still pretty flexible, especially with rules that don't matter so much to them personally. So I would expect them to switch quite fast. Stephen is following up on that work a little bit, trying to see how flexible people are at switching between different kinds of rules. Yeah, good question. Yeah.
First, congratulations.
Thank you.
It's very
Thank you.
I have a question about the same study about the compression, because the way you talked about it suggested that the compression kind of comes concurrently with the transfer to long-term memory. And it seemed like they can happen separately, like you can transfer a non-compressed representation, or you can compress it to keep it in working memory, and it still takes fewer resources. And so I was wondering if you could speak to how you know that the compressed representation is necessarily transferred.
Okay, so the question was about how do we know that compressed representations are actually transferred to long-term memory, and it's not just a compressed representation that isn't taking more space in working memory. I think we don't necessarily have a super solid test of that, but I do think that the reaction time differences that speak to that a little bit. It seems like when people have compressed rules, they don't need to do this pattern matching, and so they're a lot faster at collecting their reward, which to us suggested that perhaps a different mechanism is involved. I think, based on the past literature, that you need a compressed representation to be able to transfer it in long-term memory. And for that, we have a few tests. So some of the experiments I didn't talk about manipulated, for example, how many different goals are present, and also whether some get repeated or not. And so when the goal space is vast and you can't compress, then you don't get any benefit from repeating the same goal. So we really do think that compressed representations are a necessary condition for this transfer. Yeah.
Great talk, super impressive work. So my question was about LLP and how you think that could work for tasks where you can't really just kind of brute force your way to a solution in kind of like a tractable number of attempts, right? So in if a task here is it would take you some time, but you could do it in a few minutes, right? You could exhaustively try all 24 combinations or whatever it was to kind of figure out the right combination. But how might LLP work in settings where just sort of process of elimination isn't really sample efficient enough to achieve the ultimate outcome?
Yeah, that is a great question. So just to repeat it for the audience, it was about how can you calculate latent learning progress where the space of possibilities may be so vast, or you don't have such a clear signal of when you're succeeding or not. So I'm thinking of 2 cases that would make this harder. One is if the space of possibilities is so vast that it's really hard to calculate any progress, and if your feedback is non-deterministic, and so even if you get positive or negative outcomes, you may have still not selected the right thing. So I think there are 2 possible answers there. One, it's possible that in such conditions, people just resort to learning progress, the other type of learning progress I talked about, because that just depends on performance. So you don't need to make any brute force estimations of your latent progress. The other thing is that even when the space of possibilities is so large and continuous, people still discretize that and have heuristics to reduce the space. So think, for example, like losing your keys. In theory, they could be anywhere in the whole entire world, but you're only gonna limit your search to like a few spots that you know are most likely. And then as you explore each of these spots, you know you're likely to get closer to the solutions. Makes sense? Okay. Yeah.
Beautiful body for it. So I have two high-level questions. You know me well enough, you can probably get those. First one is, how do you, I'm tempted to ask what are the goals? I won't, ask it that little bit. How do you distinguish at the very least between goal selection and task selection? It seems like in what you were describing when studying third part, people have in some sense a fixed objective function throughout, but they're selecting between different tasks or subtasks. Is that a meaningful distinction? I'll come back to the second question.
Yeah, so how we define goals depends, I think, on the context. The definition that I used at the beginning was future state that an agent is motivated to realize. Now, this definition of goals as a state sometimes is insufficient because sometimes a goal is not just an end state, but also a trajectory, like a history of things you've done to get there. So, for example, doing a successful somersault isn't just the end state, it's the whole process. The difference between a task and a goal is also something I've been thinking about. I'm not sure that I have a good answer to that because I also think that goals kind of come with rules for how you should get there. But I think in a task that's like more of a given, and with goals, we don't exactly know for sure how that works. There's other distinctions, for example, between goals at various levels. So people may select a specific potion as their goal for this one trial, but they have the overall goal of learning all the potions. And so I completely agree that goals live in a hierarchy of spaces. And so we just need to make a choice at like operationalizing them in one specific way. But I am very interested in understanding how people decide what is the right level of analysis for a specific goal.
Okay, and then that makes sense. The second part is, in your test, you described the weights that they place on latent learning progress and each of those little things. There's things I could be playing a game on my phone right now that I'm, midway through learning and kind of maximize learning progress, and then I'm, doing this talk, and there's any number of things that could satisfy each of these, and it seems that, at least superficially, like we set different weights on those across time. So then what's that?
You mean different weights on like even the same signal?
Yeah, or I guess the alternative is to say it's always the same weight, but the strength of that signal differs. But I guess my question is kind of in the real world, is it the case that we always have the same weight on these things, or is it the case that those weights shift and then
yeah. So the question was about the dynamics of the weights that we put on different kinds of motives that let us select different goals. I don't think any of my studies speak to that. I think it would be a really interesting question to ask, and I kind of regret not having more like surveys that I collected in my experiment, because I think it would have been really interesting to ask the like trait versus state question about, are the people who just pick the same potion over and over like a certain type, or are they just not caring about this specific task? I think that's an interesting follow-up. Yeah. Yeah.
So those surveys don't have any metadata about the demographics.
We have demographics. I didn't find anything there. Keep in mind, these are also all Berkeley undergrads, which are a specific type of demographic. Yeah.
Just an amazing talk and a pleasure to see your work. Is there any experiment that you wish you could have run while you were here at Berkeley that you haven't had a chance to do?
Well, one would have been that follow-up. I guess I have a few things on my mind. One, I kind of used it as a leeway to my acknowledgements, but I do think that the social dimension is really interesting. And I am really interested in how people decide how to imitate others and at which specific levels of the hierarchy to do so, because people could copy someone else's goals, but they may want to do a PhD because their friend did one, but it could be in that same domain, it could be in a different domain, it could just be, oh, maybe I just want to learn more, but it doesn't have to be in an academic setting. And I'm really curious about how people define how to transfer inferred goals from other people to their own value system. And just so many more questions. Yeah. Yeah.
Excellent presentation. Thank you.
Thank you.
I have a question about goal selection. It seems that the goals and reward values are subjective from the individual's perspective, but the individual perspective is many times limited. In your example of the skiers, one has a goal to meet a friend, and another has a goal to win the race. But none of them has the goal of not getting injured, which is very important value. So how do you incorporate external universal value systems the individual may not have in their or individual awareness?
Okay, so the question is, how do we incorporate many different goals? I think Amitai may have a different answer to this, but but I think the world of goals and rewards is very complex. It's also kind of circular in a way, and goal define what counts as a reward, but in turn, getting rewards can determine what you select as a goal. And I also think your circumstances might make some goals more available to you at a given moment than others. And so if you put a sign as like careful, I don't know, don't fall, then the goal of not getting injured could become a lot more salient, and people may start optimizing for that. But yeah, I don't think it's easy to study in the wild, and that's why we have to dumb it down so much in controlled experimental setting with like 6 goals, and you can only choose these and blah, blah, blah. Yeah. Yeah.
There's one online question.
Yeah.
Ken Britton is asking, I've been thinking about emotions lately, and I wonder how I integrate emotional value into goal philosophy.
Thanks, Ken. Read Amitai's paper. But no, it's a good question. I haven't thought about it deeply. I think goals could also affect your emotions. There's a very old tradition of studies from industrial and organizational and social and personality psychology that studies how, for example, the speed of your progress towards your goal determines the kind of feelings you will have. I am following up on this a little bit with Bastian in a collaboration. We're manipulating how fast people are getting to a goal to see if that impacts their mood. So stay tuned. I'll let you know. Okay.
There's more questions. Let's go. Congratulate Gaia, Dr. Molinaro.
Thank you so much.
I already had the last question, but it went too late, so.
Okay. He knows where to find me.